Hi. So far we have discussed about 4 examples related to the design of reinforced concrete pad footing under various circumstances. Based on the similar set of specifications, we look into the design calculations for the pad footing subjected to only axial load. Axial load plus moment in the major axis, axial load plus moment in the minor axis, and also axial loads plus the moment acting in both axes. We take the same size of the column, same magnitude of the load, except that different combinations of the moment in the pad footing. The design step basically covers determining the nominal cover of the pad footing, proposing a suitable size of the pad footing on the basis of the surface soil pressure. We need to ensure that the surface soil pressure does not exceed the soil bearing capacity. This process of estimating the suitable size of the pad footing is based on the prescriptive method, where the estimations of the size is based on the serviceability limit state. Later, for the structural design, it will be based on the ultimate limit state. Therefore, we need to determine the ultimate soil pressure based on the ultimate load, including the self-weight of the pad footing, since we have confirmed the size of the pad footing. Later, based on the ultimate soil pressure, we calculate the moment as a result of the soil pressure, get the resultant force of the stress area, multiply the lever arms, and then multiply the width of the pad footing. We get the moment, work out the effective depth, and then determine the AS required. And then we propose sufficient amount of reinforcement bar so that AS provided is greater than the AS required. Not only that, we need to consider also for the maximum and the minimum bar area. The AS maximum prevents the pad footings from being over-reinforced in order to avoid brittle failure of the member. As for the AS minimums, is a measure to control cracking. And then, based on the ultimate soil pressure, we also check for shear resistance. There are 3 shear resistance you need to check. First is the shear plane located at 1D from the column face. We're going to check for both the major axis and the minor axis. Identify the locations of the shear plane, do interpolations, and you get the shear stress acting outside of the shear plane for you to compute the total shear force taken by the shear plane. Check the shear load against the shear resistance. This includes VRDC and VRDC minimum. Later, we need to check for the punching shear located at a perimeter of 2D from column face. We use the average effective depth. Find the locations of the perimeter 2D. See if these perimeters fall within the area of the pad footing. If the perimeter is within the pad footing area, that means you need to check for the punching shear. If it is outside, you can skip the checking for the punching shear. Now, if you need to check for the punching shear, you need to determine the effective shear areas along the perimeter plane. And also, you need to get the total shear force given by the soil pressure outside of the perimeter, and then consider the influence of the moment based on the factor beta. Check the shear resistance against the shear stress. Make sure the shear resistance is greater than the shear stress. Later, you check for the maximum punching shear at the perimeter of the column. The shear load shall be taken as the axial load. Consider the influence of the moment based on the beta. Accept that the equations used for the beta differs with the 2D parameter. We are talking about different shear plane, and also we are talking about different equations for W1. And then get the shear stress, check against the shear capacity. The shear resistance needs to be greater than the shear stress. And then later we check for the requirements for the cracking control. First, determine the thickness of the peg footing. If it is more than 200 mm, you need perimeter reinforcement to control the surface cracking at the side of the peg footing. Also consider for the maximum bar spacing, referring to table 7.3N in the Eurocode. Calculate the steel stress. Based on the table, you determine the maximum bar spacing. Compare your actual bar spacing against the maximum bar spacing. Make sure the maximum bar spacing is not exceeded. With that, you can more or less conclude the reinforcement for the peg footing. This is the overview of the design calculation steps. All 4 peg footing here will go through those calculation steps. Except that there are minor differences among them. This is mainly due to the existence of the moment in certain axes. Now, if you refer to most of the references, when they present the calculation steps, normally they only present the calculation step in one axis, which the axis is identified to be more critical. As for the calculation steps that we have discussed here, we present for both axes. The purpose is to demonstrate to you which axis is going to be more critical, so that you can look into the calculation steps and identify why are they more critical. We have summarized the critical axis under different circumstances. First, let us talk about the peg footing subjected to pure axial loads only. When there is no moment acting onto the peg footing, we will expect the soil pressures to be uniform in both axes, assuming that the stress are equally distributed. As a result, most likely the proposed peg footing size it will be in the mode of the square section. When a square section is being proposed, the critical axis is going to be in the minor axis. As demonstrated in our first example, when there is no moment acting onto the peg footing, you will observe that the main reason is due to the effective depth. In the minor axis, the secondary reinforcement bar will have to give way to the main reinforcement, leading to the main reinforcement closer to the soffit, while the secondary reinforcement lay on top of the main reinforcement. As a result, calculating the effective depth from the top surface of the peg footing to the centroid of the reinforcement, the effective depth in the minor axis it will be smaller. Because of the smaller effective depth, the contributions of the reinforcement bar reduces in terms of the moment resistance. As a result, you will need more reinforcement in the minor axis, resisting the moment caused by the ultimate soil pressure. Not only that, in terms of the shear resistance, particularly at the shear plane of 1D from the column face, the minor axis is still more critical. Why is it so? First, it is due to the shorter distance of the effective depth from the column face. Second, it is due to the narrower column width, resulting a larger effective area contributing to the shear force to the shear plane in the minor axis. Knowing that the minor axis, it will be more critical. If you design the calculations based on the minor axis, based on the calculated reinforcement bar, you will propose the same in the major axis. The pad footing will still be safe. If you check the minor axis pass, use the same design in the major axis, it will definitely pass. Now let us compare the differences between the moment in the major and the moment in the minor axis. Due to the existence of the moment, we will have the greater span of the pad footing in the directions of the moment. The purpose is to engage more areas, counteracting the moment. The process of estimating the suitable size of the pad footing might not be as direct. It starts with estimating the minimum contact area of the pad footing on basis of the echelons only. However, don't forget to take into considerations of the effects of the moment. You need to make sure the soil pressure at the surface state passes, not exceeding the bearing capacity of the soil. Because of the moment, the soil bearing capacity is no longer uniform. There will be redistributions in terms of the soil pressure, resulting a linear change in terms of the soil pressure from one end to another end, giving you a P max and P min in terms of the soil pressure in the axis where the moment is acting. In this case, the moment is in the major axis. That means you expect the major axis to have this kind of linearly distributed soil pressure, whereas the other axis would be uniform due to lacking of the moment in the other axis. Same principles goes to when you have moment in the minor axis. Due to the moment in the minor axis, the linear distributed stress will be in the minor axis, whereas uniform stress will be in the major axis. Due to the changes in terms of the soil pressure, your calculations of the moment would differ slightly. And then, when you are proposing a rectangular sections, you will need to be extra careful, especially when it comes to the width B. This is the areas that most students may have issue with. If you have difficulty identifying which B is to be used, since they are of different value, always sketch. Through these sketches, you determine which B is to be used. Let's say you are dealing with the major axis. Sketch the pad footing in the major axis. Provide the dimensions. Let's say now in this case, the width of the major axis is 2.4. When it comes to calculations of the B here, you are dealing with the other width, which is 2.2. Now, if you are looking from the other side, you will sketch the pad footing again. identify the width that you're referring to, which in this case now is 2.2 meter. When you need to use the B here, this will be referring to the 2.4. The B that you use in the major axis and the minor axis differs, and this is going to be applied throughout your calculation steps, especially when come to calculating the shear plan. Sketch the shear plan, and whenever come to the BD in the calculations, use the right B. The usage of the right B and H also happens when you are identifying your Y and also your I, the moment of inertia as well as the centroid of the rotations. If you inaccurately determine the B and H, that means the calculated soil pressure later will not be accurate. As a result, this is going to influence the accuracy of your calculations in terms of the moment as well as the shear load. This is something that you really need to pay attention. Now, how do you determine which side is more critical? Normally, the side with the moment, it will be more critical. You may observe through the calculations, since we have done both major and the minor axis. Let's say in this case, moment in the major axis, AS required will be more. Shear load, it will be higher. The punching shear stress at 2D surface in the major axis also higher, and the maximum punching shear stress in the major axis also higher. That's why if you observe the other references, they only check for one axis, which is the more critical axis. Therefore, if you have moment in the major axis, you only need to check for the major axis. Whereas if the moment is in the minor axis, you can simply check the minor axis. Now the question here is whether can you design for the critical axis based on the amount of reinforcement bar required. You adopt the same for the other axis. Personally, I would not recommend that. The main reason is due to different width of the peg footing in the major and the minor axis. If possible, you design the moment resistance for both axes. This can be seen from this example here. More critical side, it would be in the major axis. Now, if you design the reinforcement in the major axis, it is inadequate in the minor axis. That means there is still chances that if you adopt the same amount of reinforcement bar in the major axis into the minor axis, the minor axis can fail. One of the reasons it will be due to the AS minimum. If you look at the equations, you observe that the AS minimum is defined by the effective areas of the cross sections of the peg footing. Let's say now this is your rectangular peg footing. Your effective area at this plane and the effective area at this planes are different. Designing the main reinforcement bar in the major axis is this side. Your effective area, it will be this. Take the B, multiply the effective depth D. If you are designing the reinforcement bar in the minor axis, your effective plane, it will be this. Your B now is greater. That will give you a greater effective area. Because of a greater length, there will be a greater AS minimum. That is the reason sometimes the other axis, although it is not critical, may require more reinforcement bars. Not only that, because of the greater width of the longer span. They may be issued with the maximum bar spacing. Through the calculations, you need to determine the stress in the steel and then determine the maximum bar spacing. Let's say now we are providing the same amount of reinforcement bar in both axes. The maximum bar spacing may pass in the shorter span, might not pass in the longer span. But what is for sure? You can choose to only check the critical axis for all the shear. To make it simple, to prevent the chances of underestimating the amount of reinforcement bar as well as the maximum spacing of the rebar, you might need to do both axes for the moment resistance as minimum and also maximum bar spacing. As for the shear, it is sufficient for you to check the critical axis. If the critical axis check pass, the chances of the non-critical axis passing would be relatively high. Now, if you are proposing the rectangular peg footing, you need to pay attention on one more issue, which is you need to have 2/3 of the reinforcement of the shorter span concentrated within the mid-band width of C plus 3D as a part of the requirement to make the reinforcement to be more effective in resisting the moment due to the soil pressure in the transverse directions. This is not applicable when you are proposing a square section. And then if you observe 4 different examples here, you realize that sometimes we don't need to check for 2D perimeter punching shear. For example, this and this. However, sometimes we will still need to check this. You might want to ask, why changing the directions of the moment can result in 2 different outcomes? The main reason lies within the orientations of the column. In our case, the column size is 300 times 150. One side is wider, another side is shorter. And then we are defining 2D from the column face. In the case that the moment acting in the major axis, we need to check for the punching shear at 2D perimeter. It is because when the rotations is in the major axis, we're going to provide a wider peg footing in the directions of the moment. A wide column width plus the distance of 2D, you will have your perimeter of 2D still within the peg footing. As for this side, shorter width of the column plus 2D. If it also falls within the peg footing, then you need to check for the punching shear at 2D. Now take this as an example. Now you will have moment acting in the minor axis. As a result, the peg footing most likely will be rectangular in the directions of the moment, resulting a shorter width from the column face here. There is high chance that the parameters go outside of the major axis. When the 2D parameters go outside of the peg footing, that means you don't need to check for the peg footing. This is what we observe from the calculation steps. And then how about the absolute plus moment in both axes? In this case, we use the same magnitude of the moment. This might not be the case. Sometimes it can be greater moment in the major axis. Sometimes it can be greater moment in the minor axis. If two sides having the same moment, most likely it's going to end up to be a square section. If either side having a greater moment, it may end up to have a rectangular sections in the directions where the moment is greater. Now in this case, when you have moment in both axes, it is harder for you to define the critical axis. Normally, the critical axis will go for a greater moment. If the moment in the major axis is greater than the minor axis, then it is likely the major axis will be more critical. Otherwise, minor axis will be more critical. In this case, when you have moment in both sides the same, we will follow the rules of the square sections, where the minor axis it will be more critical. The main reason it will be due to the effective depth. Smaller effective depth will require more reinforcement bar to take the moment, and also will give you a less effective shear regions to take the shear load. Personally, I would recommend that if your peg footing designs will have moment in both axes, regardless the magnitude of the moment, better you check for both axes. Sometimes it is harder to tell which side it will be more critical until you've done the calculations. So in order for you to design this, you need to first understand the characteristics and the unique calculation steps of these first three examples, as you need to pay attention of their uniqueness when come to the design in their respective axes. I believe by now, going through these 4 examples, you have a better understanding in terms of the design of the peg footing under different circumstances. You can even try for some more examples of this, having moment in both axes, except now you have a greater moment in the major, and then try another example, you have a greater moment in the minor axis. This will lead to you a rectangular peg footing, and you will need to refer to the unique calculation steps as a result of the rectangular sections in designing those examples.